Welcome everybody to geohug, and today it's going to be such a good one. I'm super excited that we have John McGaughey with us today. So John is the founder and president of Mira Geoscience, a geoscience software and services company in Canada and Australia. And his focus is multidisciplinary integration for better decisions across mineral geoscience, from technologies, business applications, and to help make better decisions. So he has received multiple awards for his leadership in data integration and interoperability. So with his expertise, it is going to be brilliant learning from him today about what the data has taught him with perspectives from a career in exploration data integration. So thank you so much, John, for joining. It's just awesome having you here today.
Pleased to be here, Jessica.
Awesome. So yeah, I'm very curious, a big long career in geoscience. What pulled you into geoscience to begin with?
Oh, to begin with, I started out in electrical engineering, and after 1 year of that, I accidentally got a summer job way up in the Arctic doing uranium exploration. I was 20 years old and flying around in a helicopter every day, taking lake sediment samples over a big area, and that just got me hooked. I was lucky because at that time, I don't think it's the case anymore, but in Canada, geology was a core part of a first year engineering curriculum. And otherwise, I'd never taken a geology course before, and I was in electrical engineering. And boy, that summer flying around the tundra got me hooked, and I decided I didn't want to spend my life in a cubicle. I ended up spending my life in a cubicle, by the way, but I had quite a few years of traveling around and doing interesting things. So that's what got me started.
That's brilliant. The accidental geologist, that's so good. And so you probably have traveled far and wide. What have been some big career highlights for you?
Well, I think I've been lucky in particular because I've had quite a variety of things. I started off in the oil and gas business. So I worked for Shell Canada and Chevron Canada in Calgary. And then my first permanent job after university was working for Schlumberger as a wireline engineer in the Gulf of Suez offshore oil rigs in Egypt. And after that, I decided to go back and do a master's, still in oil and gas. I was in seismic reflection processing. And then following that, I did a little bit of a twist. I got talked into doing a PhD also in seismic, but now applied to rock mechanics and in mining. So it got me into seismic tomography, which is seismic inversion, but for rock mechanics applications, which led me to a job in the mining business with Noranda at their technology center in Montreal back in the day when big mining houses had big R&D complexes. There were about 250 people there when I worked there throughout the 1990s. And it was just a fantastic place to learn, traveled all over with them, all their mine sites, got into exploration more deeply with them, and ended up focusing mostly on mineral exploration, but I still work in rock mechanics as well, as does the company, always focused on data integration.
Yeah. Wow, there you go. You've done all sorts of things. That's really cool.
Yeah.
Interesting. And I'm very curious, it's even a surprise for me, what pet rock you have for us today.
So you asked me to bring in a pet rock, and as I thinking about it, I don't have a rock collection. I know that's probably sacrilege in the geosciences, but my wife, is a fashion designer, and her father was a mining engineer, and she grew up with a massive rock collection in her house, and she was like, "Nah, it's not happening here." So no rock collection in my house. However, we do have a fountain in our backyard with a little rock collection around it, rocks collected from a beach by our summer house where we spend our summers out on the East Coast. So very meaningful to me. So we've picked up rocks on that beach over the years and put them around the fountain, and they're all here. They're not exciting so much as a rock
Oh,
itself. It's a quartzite cobble, I guess, a rounded cobble that's come out of a big, thick cobble conglomerate unit that's right by the sea where we are, and the tide washes the stones out of it and makes really a beautiful array of stones on the beach. So we think of where we like to spend our summers by looking at our little rock collection by our fountain in our back garden.
oh, I love that. That is
Mhm.
so nice. That's,
Mm,
yeah, sentimental. Sentimental
sentimental.
pocket friend. Yeah, I love it. That is perfect. Well, thank you so, so much again for being here and taking the time to talk to us. Yeah, if you want to share your screen and we'll get stuck into it.
Okay, so as I was saying there, I've spent really most of my career thinking about data integration, not just geology and geophysics, although that will be the main thing I'll be talking about today, because this is mineral exploration, but certainly on the rock mechanics side, we think about data integration as well, how to bring together all sorts of engineering data with geology data and combine it, typically for geotechnical hazard analysis, which actually has a lot in common with exploration targeting. In both cases, you're looking for something anomalous, where it is, and trying to characterize it based on multidisciplinary data sets. And I'm going to start off by firstly showing you a picture of the beach where my pet rock came from to give you an idea. So this, here, let me see if I can get the pointer, laser pointer. Yeah. So this isn't about my talk, but it's about my pet rock. So this formation here is called the Quaco Formation, not the Quackoff Formation for you rot nesters, the Quaco Formation. And it's this pebble or cobble conglomerate that is beaten by the tides into this rocky beach. And this is in the Bay of Fundy in New Brunswick on the east coast of Canada, which has the highest tides in the world. And at this spot where we are, the tides are around they go between 8 and 11 meters vertically, depending on the time of the month. And up at the head of the bay, they get up to about 16 meters. So it's a pretty interesting area. And just to let you know where that is and where I am, I'm talking to you today from our office here in Montreal. And this red dot over here is where my pet rock is from on the coast of the Bay of Fundy. That's the Bay of Fundy here between Nova Scotia and New Brunswick. And I'll be showing you some bits and pieces of data in this talk from some other areas on this map from around the Bathurst mining camp. So these are Ordovician rocks, a classic VMS mining camp up in this area here. I'll be showing you some examples from the Abitibi Greenstone Belt of Western Quebec, this area here. I think I've got a picture early in the talk. Well, I know I do, from Kid Creek Mine, which is here in Timmins, Ontario. And then I've also got a little bit of stuff to show you from around Sudbury, Ontario. So that's where I am and where some of the data is from. To give you an idea of scale, Montreal to Toronto is 550 kilometers by road. And depending on the traffic, can take an infinite amount of time to get there. So what do I mean by data integration? So I've written it down here, turning diverse measurements of the subsurface into a single internally consistent representation that supports understanding and decision making. So understanding and decision making is where we're trying to get, of course, with our data. And by diverse measurements, in the mineral exploration case, I'm speaking really of, what we all know, geological, geochemical, geophysical data. And by a representation, I mean a map or a model. So just the things that we're used to every day. And you might think, well, turning geological, geophysical, geochemical data into a map or a model to support understanding and decision making is just what we all do. But is it really is the question I would ask, or is it really most of the time? And I think the answer is no, at least not in a thorough way. And and the part that's missing is right in the middle of that quote. It's where it says internally consistent. So not that hard these days to make a map or a model, but it's quite another matter to make an internally consistent map or model. And I'm going to be exploring that notion quite a bit in the talk. What do we mean by an internally consistent representation? And what does that give us? What's the value of that? So let me start with a picture from, this is a GoCAD model from Kidd Creek Mine. That's the Kidd Creek ore body, this steeply dipping red thing here, enveloped by some formational contacts. And then we see some other formational contacts in and around it. So a real brownfields exploration setting. Cutting through the geological model, you see a series of two-dimensional sections. These are sections from a large-scale DCIP survey that was done by Quantech. This is an interpretation that was done around 25 years ago. So this is an old GoCAD model, and at the time we did this, we were really excited to be able to bring geological and geophysical data together into a model. So there we have it, and what I'm saying on the left-hand side here is something that I'll get back to also in more depth in the talk, is how geologists and geophysicists represent their data in the model. And I'll talk about lines and surfaces versus what I affectionately call blobs. So lines and surfaces are what geologists use. So lines on a map or wireframe surfaces in a model. So these are vector representations in a model. That's how geologists create their view of the subsurface. Geophysicists tend to work in rasters primarily, so they grid data on the map rather than draw lines on the map. And they produce either gridded vertical sections like that shown here in 3D, or perhaps 3D full block models. And these are either representations of geophysical data itself, or now more commonly of an inversion, so of a physical property. The Earth, of course, is neither vector nor raster. It's just the Earth. Vector or raster are just geometric supports that we give our data in our model. And what I came to realize early on was this is pretty good. There's value in this co-visualization of data. Definitely helps, better than not having this co-visualization of data. But once you start really staring at the picture, you realize, this isn't right. There's inconsistencies everywhere. How can the physical properties that are apparently represented in these geophysical sections be so smooth and how, they just bleed across these formational contacts that we really understand to be discontinuities in the geology, therefore discontinuities in the physical properties. So you're really looking at two different worlds here, and of course they're both wrong. I mean, no model's ever right, but It's one thing to have two models superimposed on each other where they're both wrong. And another if you can actually force these to be at least consistent with each other. So it still may not be right, but at least you have a model that hangs together. The geology and the geophysics speak to each other within the same model. They're consistent. They give you, as an interpreter, something you can really rest on and say, okay, this is our current hypothesis. This is a consistent model. The geological data, the geophysical data, both support it. We have one model supported by multiple lines of data. Let's work with that until it's proven wrong with a new drill hole or new idea, perhaps, and then we'll change the model. But the idea is that you have a single model supported by both data sets. And I learned as a geophysicist early on, when we were doing some ore delineation work using crossflow methods, geophysics, that it was really hopeless to show your cross sections with these blobs of red and blue and green colors up against formational contacts and faults drawn by the geologist with a pencil. So the geology looks super high resolution, even though it was really just connecting, borehole markers with a pencil. And the geophysics looked hopelessly vague and blurry, even though, really they were both interpretations of data from the same Earth. So this is one of the lessons I learned really early on, is that if we're going to have success with these modern methods of inversion and 3D interpretation and modeling, we're not really going to get anywhere unless we could make our data speak to the same model. So the data here look good. Visualization looks nice. It's useful. There's value in the co-visualization, but there's not nearly the value that we could get if we actually got a model that was consistent with both pieces of data. And that got me looking at what they were doing in the oil and gas business. And there they were taking a different, and what I thought at the time, and actually still think, is it was a much more sophisticated approach. Earth model synthesis. They call them these models that are supported by everyone's data, common Earth models or shared Earth models. This is one of the pioneering papers in it. It's from back in 1997. So this kind of stuff was all the rage 30 years ago in the oil and gas business. People were just developing the workflows and technologies to support this very idea I just talked about, having a single model shared by the geologist and the geophysicist. And these workflows, they would trade in effect phases of working on the same model with individual data sets back and forth around the loop, so that at the end of the day, they would have a single model that the geological data supported, the geophysical data supported. Everyone could sign off on it. It may not be right, but it was represented the best they could do at the time with the data they had, supported by everyone's data, and was consistent with whatever the geological conceptual model was of the area. And from that came, in the oil and gas industry, this idea of asset teams and integrated interpretation. So the asset team is multidisciplinary: geologists, geophysicists, petrophysicists, reservoir engineers, organized around the resource, around the field or the prospect, not organized by discipline. Right? So everyone's sharing the model, and it's fully integrated between the disciplines. How that worked in practice, unfortunately, didn't and doesn't translate directly to the mineral industry. And that's because of the nature of our data, our geophysical data, which is not seismic data most often. But in the oil and gas business, it worked sort of like this. Geophysicists would start off, interpret the seismic data. The seismic data is an imaging technique. So the nice thing about seismic data is that it can be interpreted directly in terms that that are familiar to the geologist, those vector or surface or terms, so horizons and faults directly. So those surfaces would be handed off to the geologist to be integrated with the well logs, the core data, the geological concepts. The geologist would build a 3D geological model with that geophysical interpretation as support, define the details in it, the formations, the reservoir architecture. And you have this collaboration where the geophysical interpretation constrains the geometry and the geological reasoning or conceptual model imposes stratigraphic and structural coherence to the geophysics. So the geologist is responsible for the geological model, but the geophysicist provides the geophysical framework that makes it possible. At the end of that process, at the end of that workflow, you have this common Earth model or shared Earth model, which again is this single model, which represents the best current understanding of the resource. It's consistent with everyone's data and consistent with the conceptual model. Again, it may not be right, but it's like a scientific hypothesis. It makes sense. It agrees with all the data. It's falsifiable or verifiable. You can drill a new well, collect new data. If that new data points out inconsistencies or flaws in the model, you update the model just like you would update a scientific hypothesis. It's a really strong conceptual framework for integrating data. Can we do that in mineral exploration? Well, we've been trying for quite a while, and the short answer is yes, we can, but it's not easy. And I would make the point that in almost all cases, even though it's not easy, it's worth it. It provides great value compared to isolated or siloed interpretations that are visualized together. So I wrote a paper back in 2006, taking that concept from the oil and gas business, the common earth model, and I hoped it would be a revolution in mineral exploration data integration. And that this paper is actually being quite well read. It's a well-cited paper. It was published in a special volume, GIS for the Earth Sciences, from the Geological Survey of Canada. And it basically went through that process I just described in the oil industry, translating it into the mineral industry. What do we have to do? So I'll give you some examples in the rest of the talk of how we can approach that in mineral exploration and talk a little bit about the value that it gives. So what the data taught me, conceptually, visual data integration is nice, but to me, it's very 1990s. It's certainly what we were doing at Noranda in the 1990s. And again, we thought we were pretty sophisticated, visually integrating geological models with geophysical inversions, doing nothing really to quantitatively build models that were consistent with both the data. It was really separate, siloed interpretations brought together visually. And that is not where most of the value lies. And I think it's a bit of a shame that that's still, for the most part, what's done in mineral exploration. Not all the time. And there are some great examples of what I would call doing it right. And a lot of people are doing that now, but it is a bit of work. Interpretation is a modeling problem because falsifiable models are necessary to validate the interpretation. And what I mean by that is interpretation of geology, geology data in terms of a model that you can use for, say, targeting, is it's a modeling problem, because to do it right, you need to be able to test that model against other data sets. And that's really the paradigm around this common Earth model or shared Earth model concept. You build a geological model, and then you validate that geological model against, say, geophysical data. That makes geological interpretation, by its nature, a modeling problem in the sense that you're creating a model and testing that model. And then the modeling itself is an interpretational problem because it requires geological insight. And we have to beware of the mathematical or heaven forbid, the AI approaches to creating models as a shortcut around the sort of hard work of thinking through the geology conceptually, and just relying on the math or the AI to create the model. And I don't think that's done blindly much. I've been following a bit some of the AI work in generative model construction in the oil and gas business. And there's some, interesting advances there. I think they're a long way from creating reliable models with that. Maybe that day will come. But we really have to beware about the mathematically created geological model, especially in this age of implicit modeling. Implicit modeling is great because it's convenient. You can generate a model really quickly, but the model is guided by the mathematical formulations that are at the heart of the algorithms that are out of the geologist's hands, rather than in the old days when you're building models explicitly and the geologist was having to think it through and guide it methodically, build that model. Took a long time, was a pain. Hopefully you got the model you wanted. And hopefully you got a model that was quite geological. Models look pretty mathematical these days in many cases, and you can see a lot of artifacts of the algorithms used to construct them. This interpretation, modeling, validation cycle, this workflow that comes from the oil and gas industry, can really only be addressed with this common Earth model or shared Earth model concept. You need that representation as the common framework where the geologist and geophysicist get together and work on that model together, ensure it's consistent with their data, and in effect sign off on a model as being the best model that we can create with the data and thinking that we have today. It's a model that's falsifiable with the next drill hole or the next data set we collect, and that's fine. We take that next drill hole or that next data set and we correct the model, but at all times we maintain that consistency with everybody's data. Some practical notes on what you need to do to achieve that. You need to pay attention to physical rock properties. Physical rock properties are what connect geology to geophysics. Geophysical data is only sensitive to changes in physical rock properties in the subsurface, and physical rock properties, of course, are a consequence of the geology. So that's the connection between geology and geophysics. And when I say they need to be taken seriously, not literally, what I mean is they need to be taken seriously because they are the link, and you need to think about rock properties when you're doing this kind of integrated interpretation in mining, just as in oil and gas. I say not literally because physical property data tends to be a mess. That's just the state of things, both from a collection calibration perspective and also because they're a bit of a mess in the earth itself. They're multi-scale, they're anisotropic, they're difficult to work with, they're noisy, but they're important. The physical properties really do tell the story of the rocks, and the physical properties are exactly the thing that determine the form of your geophysical data. You need integrated technology platforms. So I mentioned GoCAD in the oil and gas industry. There are multiple platforms. GoCAD is one, Petrel's the most common one. These platforms are built for integrated interpretation, for data integration in the model. These are not, as I call it, connected but siloed platforms. They are not a geological modeling system in which you're importing geophysical data to look at it. That's the visual integration that we need to get beyond. What we're talking about here are platforms that treat geophysical and geological data equally. They're not a geologist platform or a geophysicist platform. They're an explorationist platform in which all the disciplines can work. It can be done with current tools, but it's not easy, so it's mostly not done. I think it's really as simple as that. I think it could be done much more often. It's not, say it's not easy, but it's also not that hard. What you need is some good technology and some skilled people, and it can absolutely be done. And we do it all the time within our company. We have a consulting group that does it. There are other people out there who do it as well. I just know from what I see, it's not done by and large. It's not the majority of work done, and I think it should be the majority of work done, particularly on assets where a lot of money is being spent for ore body knowledge. In many cases, it should obviously be done. Brownfields exploration should, to me, obviously be done. Should be done. You need the technology and a multidisciplinary team, but there's really no reason otherwise to not do it. So some examples of what I mean. So here's an example from the Geological Survey of Queensland. This is the Mount Dore area up around Mount Isa, that area. So here we have a district scale model, so a true exploration model, and there's multiple data sets there. You can see there's electromagnetics, gravity data, magnetics data, there's geological data, mapping. There are also soil survey data, there's MT data, all sorts of data. So a real great collection of data, something, crying out for data integration. And what we do before we think of doing anything in terms of targeting or thinking through the interpretation is we just work really hard on creating a 3D common earth model that's consistent with all that data, right? So we'll be talking a little bit more about how to do that, but this here is to inspire you to think it can be done. And what we're showing on the right is a gridded version where the colors in the cells there are lithology. So it's done at a certain scale. And that is a model that's consistent with all of those input data sets. So what that means in practice is that this model has lithology codes in the blocks, but it also has density, magnetic susceptibility codes. And if you forward model those physical properties, you will recover the data sets, right? The geophysical gravity data set will be recovered by forward modeling. The density in this model, the TMI or magnetic data set, will be recovered by forward modeling the magnetic susceptibility in this model. That's what we mean by a common earth model. The geologists and geophysicists can all sign off on it. I'm not saying it's right, it's certainly wrong, but it's the best we can do. And it's a starting point for all future work with that model. For example, targeting. So this is prospectivity mapping. And it's really, to me, a critical step to start off with that geological block model. So here we have the data. We create the common earth model, which has within it 3D density and susceptibility inversions. And, I know the scale is small here, but I think you can probably see the trace within that block model, within those density and susceptibility models of the lithologies themselves, right? So these aren't unconstrained, just super blobby inversions. These are inversions that are constrained. So you see some of the structure of the geology. And from that, we go on to the prospectivity mapping. However, that's done typically through machine learning these days. This isn't a talk on how to do prospectivity mapping or machine learning, which can be an endpoint of data integration. Makes total sense. But the point I'm trying to make here is that if you're bringing data into a machine learning algorithm, such as geophysical data, you should not bring in the geophysical data itself, what you might call the raw data. The magnetic field that's collected by an aircraft flying over an area cannot be directly co-located with a rock type or soil geochemistry or any other property of the actual rocks beneath it, right? The magnetic field is a complex product of the entire volume of the model, as is the gravity data. And geophysical data in general is data that is sensitive to volumes in the geological model. So you've got to try your best to build an optimum physical property model through inversion from those geophysical data sets if you're going to co-locate it to geological properties to run something like prospectivity mapping. And you have to be very careful, because if you're doing inversion, we'll talk a little bit about this later, but all the geophysicists who may be listening know that geophysical inversions are non-unique. So, for example, there's an infinite number of density, 3D density distributions that would forward model to the same gravity data set. That's what we mean by non-unique. So you have to do your absolute best to work through an optimum density model before you introduce it into a data integration statistical process, a pattern recognition process, like machine learning for prospectivity mapping. So this is where the value comes. If you do the work early to build a proper common Earth model, the payoff will come when you do the prospectivity mapping, right? This is absolutely garbage in, garbage out, the prospectivity mapping. And if you're not building this model correctly in the first place, it's garbage in. We've been doing this for quite a while in 3D. This is just another example. This is from the Abitibi in Quebec here in Canada. And again, what we're trying to do is this is data integration. This is a primary application of data integration. We're trying to define drill hole targets as a function of space, X, Y, Z, and doing that as a function of all of these different multidisciplinary data streams. So we're trying, and what that means in practice is that at every cell of this block model, we've got to build variables for rock type, alteration, structure, how far are we from the nearest synvolcanic fault or whatever, geochemistry, mineralogy, the physical properties that come from the geophysical data. So if we're starting off with a block model containing all of these properties or features in a machine learning sense that don't consistently hang together in a common Earth model, then what are we doing? How can we hope to recognize the patterns in there that will reveal the optimum drill hole targets? Okay. So we have to really work hard at building consistent models, and that means any block in here should have, if it's got a density and a magnetic susceptibility, well, that density and magnetic susceptibility should make sense for the chemistry, the alteration, and the rock type that are also contained in that block. So here's that idea specifically, and this is, I think, a really good way to look at an integrated model or common Earth model. What we want to do, and you can see, actually, I've been talking about prospectivity, but I think you can see here that directly the applications to ore body knowledge as well. We're trying to build a picture of each block or each point XYZ in a 3D volume, right? So we have the 3D volume that is our Earth model. Here we happen to be representing it as a block model. Doesn't have to be a block model, but that's what we're doing here. And what we're saying is that that block model has a story. Each block has a story to tell about itself. How close is it to the nearest fault? Does it have a fault going through it? What's its lithology? What's its alteration profile, its mineralization, physical rock properties? If you're into geomet, what are its geometallurgical properties? Thing is, every one of these blocks can have all of those different variables in it, and those variables have to hang together, right? You can't have a density of, 3 or 4 and call it a sandstone. It's got to work across the spectrum of the properties in that model. So that is a common Earth model. Once you've achieved that, again, might not be right, but it's the best you can do with the data you have. And everyone can sign off on it as such. And here it's shown in a Venn diagram form where you have, each dot here is a model on that. So here we've got 3 models that are geologically acceptable. Maybe all of those 3 models came from, your favorite geological modeling platform, different runs, different people modeling it. They're okay. Everyone thinks they work with the drill hole data and then whatever other geological data you have. And then you've got other models that are geophysically acceptable from whatever geophysical data you have, treated in isolation from the geology. And then separately, you have geochemical models. So if I talked about having geological models in which we import geophysical data and show that geophysical data visually superimposed in the geological model, like we did 25 years ago at Kid Creek. And we're pretty happy about that because it looks cool and we can, spin it around and it is informative and we do get value from it. But where we are with that is we've got this geophysically acceptable model here and this geologically acceptable model here, and they're really in two different worlds. And what we have to do is find models, and of course there will be more than one of them, but at least find a model that sits at the intersection of our data. So that's just another way of looking at the same thing. We want to find the common Earth model that satisfies all of our data. So a model supported by all: geology, geophysics, physical properties. Why do we need to go beyond visualization? Because it's important to validate geological interpretation. Simple example, and people should be doing this more often. You build a geological model, today's implicit modeling, press of a button. Maybe it's a bit more complicated than that, but pretty quickly you build a geological model. If you have magnetic data or gravity data, almost everybody has high quality aeromagnetic data these days. If you have high quality magnetic data, well, then you should take that geological model that you produced with your geological modeling platform, attribute it with magnetic susceptibility, forward model it, and compare your forward model to the magnetic data you have. And if they don't match, and they won't match, it's not really a question of if, you have to ask the question, why? What's wrong? Assuming the data is right, the geological data and the geophysical data is right, that means the model's wrong. Why is the model wrong? How can I improve the model? That's the common Earth modeling process. And it's really simple to start. All you need to be able to do is build a geological model, attribute it with a physical property, and forward model to a geophysical data set that you probably already have. And it's probably magnetics, and it may be gravity as well. Potential fields are the easiest ones to do. Compare the forward model to the data. They won't match. Start asking yourself why. Start asking yourself what is wrong with your model. And there will be something wrong with your model. So it challenges geological hypotheses. And in doing so, it just leads to better targeting and better ore body knowledge, and that's where the value comes. So digging a little bit deeper, I want to talk again about lines and blobs. So the lines are the vector representation. There's surfaces, wireframe surfaces in 3D, and the blobs are the red, green, blue, and yellow blobs that geophysicists love to produce, either by gridding data or inverting data. So geologists draw lines, geophysicists compute or create blobs. Both interpretations are consistent within their data silos. Are they consistent with each other? Can we do better? So I'm asking the same question again, but in a different way. But you should ask yourselves these. I always ask myself this kind of question when I see maps like this. So this is a geological map. It doesn't matter from where or what it is exactly. I just pulled it out of a paper I saw recently. And then there are three geophysical maps here, right? But these aren't geophysical data. These are actually physical properties. So they're from an inversion. So this is resistivity up in the top right, and chargeability on the bottom left, and magnetic susceptibility here on the bottom right. And we see these models, we just go, wow, there's like, what's going on here? So the geology is all these hard contacts between units. These are the lines that demarcate the structural breaks and the formational contacts. And then we have the physical properties just bleeding hopelessly across them. You see a bit of the sense of the geology in those geophysical blobs, but not a tremendous amount. And I would expect to see much harder boundaries in the geophysics if the geophysics was realistic, where we actually have geological contacts. I'm not saying these geological contacts are in the right place. That's the other thing, of course. The geological map or model, is just that, a map or a model, and its control points are maybe dense or may not be dense, and if they're not, there's a lot of interpolation there as well. But my problem here is just the representations are so starkly different when it's after all the same Earth. And in both cases, there's really physical property differences underlying it, right? So the geophysical data, the blobs, are very directly responding to variations in physical properties. But here too, at the top left in the geology, we would ordinarily expect physical property contrasts across structural and formational breaks. So it's a bit unsatisfying. And so what's going on here? So we have geophysics, geology, and these days mathematics imposing itself on both, which is a good thing. Mathematics is foundational to modeling, and modeling, validation checking is at the end of the day a mathematical as well as a geological enterprise. But here's what's going on. We have geophysical data here shown as a magnetic grid on the top left being processed through an algorithm, and out comes a 3D block model of magnetic susceptibilities on the right. So this is the classic unconstrained inversion. This kind of thing's been around for 30 plus years, very widely deployed and to good effect. What it tends to do, at least for potential field data, is show, blobs in 3D in the inversion under the same blobs that you already saw in 2D on the map. But it does give you some insight for sure into the 3D world that you weren't getting from the grid or the map. So it's a good thing to do. But it's a mathematical construct. It's forced to be smooth for convenience, for the convenience of solving the equations. Here, the inversion equations, this is a so-called objective function, which has to be minimized. There's non-uniqueness. The way they handle that mathematically to get a stable solution is to smooth the model. So that's funny because we know that we know sort of a priori that physical properties are discontinuous in the Earth. They will change mostly across contacts. So we know they're not really smooth, yet we impose smoothness mathematically out of convenience, just as we impose smoothness in the gridding out of convenience. So we're smoothing because the mathematics tells us to, and it's what we can do conveniently, even though we know probably physical property distributions in the earth aren't particularly smooth. Geological data in the age of implicit modeling. Here we have some structural markers. Apologize, this map is not that clear, but we have some line work. So there's some control on the geological map as well as structural markers. Here we have the famous radial basis function way of interpolating a scalar field through a 3D volume. And then we extract isosurfaces there as geological contacts. That's how we make our geological contacts and our faults in an implicit model, and then we cut them against each other. So what you see in the 3D block model there is the scalar field. That's the actual radial basis function interpolation. Doesn't have to be a radial basis function either. Some programs do it with kriging or other methods. But you need a smooth interpolation. So again, smooth for mathematical convenience. And then from that, we extract this smooth wireframe and say that's the contact. So in both cases, we're using mathematics of convenience and our convenience to make these problems tractable, which would otherwise be really hard to solve. And we get models out, and the geologist gets the vector model of the surfaces, and the geophysicist gets the blobs. And boy, what's the connection? What's the connection mathematically, right? I mean, actually, the connection is physical properties, but how to create a system of equations mathematically to solve both is a problem that has not been solved yet. So we have to inevitably take an iterative approach and cycle through these until we get to something that approaches convergence that we're satisfied with, which is exactly what they do in the oil and gas business too, in their common earth modeling workflows. Just a quick word on non-uniqueness to remind the non-geophysicists listening what that is. This is resistivity data. So this is two-dimensional resistivity survey, and you can see on the right-hand side pseudo sections. For those of you old enough to remember pseudo sections, probably young people may not know what pseudo sections are anymore, but they're a representation of data. So this is just showing resistivity data as collected out in the field and plotted in a certain way to approximate roughly a cross section, hence the name pseudo section. And I'm showing the same thing. I can't remember where this came from. So sorry, there's no attribution. It's not from me, it's from some publication, but it's showing the same thing 3 times. And then that same data is being inverted 3 times, as shown on the left. And you get 3 wildly different answers depending on the parameters you put into smoothing operators in the inversion. So in this case, we said, oh, give it vertical structure at the bottom, the middle, give it horizontal structure, the top, don't make any preferential structure, just let the blobs be blobs. And the thing is, in all 3 of those cases, those are all equivalently good models. They all forward model to the same data. So that's what we mean by non-uniqueness. You could create any of these Earth models here in 2D, and of course the same applies in 3D from a given data set. So that's sort of how bad the problem can be at the end of the spectrum. Geophysically, and in practice, it's not usually that bad. We have more of an idea. So one thing we can do, though, is constrain the inversion, and the people, the professors who initially came up with the inversion algorithms we use today. First and foremost, perhaps amongst them, Professor Oldenburg at the University of British Columbia, from which this is drawn. This is our work, but using MAG 3D code from the University of British Columbia. Always had built within the formulation the ability to constrain the inversion, and you constrain it in different ways. And constraining could be through smoothness constraints, showing preferential smoothness directions, like I showed in the last picture, or it could be directly through geological knowledge that you have. So this was our first try at making a common Earth model. Really, so we took a geological model. So this is a GoCAD model. This is regional. This is about 10 by 10 kilometers ish, or 10 by 15. Abitibi, Greenstone Belt again, northwestern Quebec. And we have this formational and structural model up here. We attribute it with physical properties on our best guess of magnetic susceptibilities. We take the gridded, filtered mag data, properly processed, and then we invert it. So we get a constrained inversion, looks like this. And now we can hang our geophysical model in our geological model, and we see traces of the geology in the geophysical result. And that's pretty good. So let me show you an example here, more directly comparing an unconstrained inversion, so letting the blobs be blobs, so to speak, and then on the right, a constrained inversion, where we're saying, no, let's not let the blobs just be blobs. Let's try and force something. So what we're trying to force is a closeness to that starting or reference model that we supplied it with. So we said, oh, well, here we have a magnetic dike, so we expect the magnetic susceptibilities to be high there. So try not to deviate far from that in the inversion. And you can see it's done that way. So we have that red line nicely following the dike. But then we still have blobs in other places. And that's interesting. It's what that's telling us, for one thing, is it's saying, well, I can satisfy your geological concept of a dike being there, but you've got other stuff going on in your geological model that's not at all accommodated by the geophysical data. So you better do some thinking about your geological model. And that's all of these, blobs here. So there's all sorts of stuff going on geophysically that wasn't accommodated in the geological model. So that gives us the idea, okay, we can go back, take another step, cycle back in the workflow, update the geological model. This is that first step of validation I was talking about. People should be doing this routinely. I don't think they are. I think they're doing it sometimes. But if you have a geological model, I think the first thing the geologist should do is sidle up to their friendly geophysical colleague and say, could you please validate my geological model? And the geophysicist will be happy to oblige, and no doubt respond by saying, well, sorry, your geological model's wrong. And the geologist will say, okay, well, what do I need to do to fix it? And the geophysicist will probably say, well, let's have a look and talk about it. And that's good. That's what you should be doing. You should be talking about it, coming together over a shared model. But this has limitations, the constrained inversion approach, because it's still saying, well, it's a world of physical property, blobs, and I don't think it is. So our second try, stochastic approaches, and we played around with these for quite a while. This is a paper that I published with a colleague, Miguel Bosch, who was the first author, back almost 25 years ago now. It's from the leading edge. This is in 2D this is joint inversion of magnetics and gravity, constrained by a starting geological model and constrained by a given joint probability distribution of density and susceptibility, as shown here on the right. And this gives you interesting things. It gives you, in this case, tens of thousands, and it could have been millions of models that match the data. So these are profiles showing that the forward model data matches the observed data. And these are, each one of these tens of thousands or millions of models, has a picture. It's a model. It's a model of density, susceptibility, and rock type. And when you've got, these suites or ensembles of models, and you can start looking at probabilities. And I became dissatisfied with it. I think stochastic approaches certainly have their place, and I'm not here to partially judge them in total, but I became they fell out of favor with me. I just thought they weren't exploring the model space properly, getting all sorts of stuff that was completely unrealistic. And I thought, and it's still representing the Earth as way blobbier than I think it is. Let's try to cut to the chase and try to make these models more directly geological. So that leads us to the third try, which is still where we are today. And I think this is the right approach. Still a bit of work and takes knowledgeable people and the right tools, but we call this simply integrated interpretation. I don't have a better term for it, but it's driven by this key insight, which is really completely simple. Geophysical data is primarily determined by the geometry of geological boundaries. What does that mean? That means that physical properties, how they're distributed in the Earth, is really controlled by the geology, controlled by the geological discontinuities of structural breaks and formational contacts, and physical property distributions in the real Earth are not these kind of blobby things that we get out of conventional geophysical inversions. And the thing is, we knew this all along. And I think inversion, for all the good it's done us and for its necessity in this integrated interpretation workflow, can still and has led us astray a bit because of this forcing these smooth models out of this mathematical convenience to solve the inversion or stabilize the inversion equation. The only reason I put this picture up here, and again, this is kind of randomly drawn out of just a journal, but it shows what we knew all along. We got these geophysical maps. This is magnetics, and we're drawing lines on it because the geology, we know that geology is discontinuities, and we're trying to see those discontinuities through the patterns here, but we know that fundamentally, the Earth is discontinuous. And we do that now primarily still through GoCAD. GoCAD, coming from the oil and gas industry, was built for this shared or common vision where neither geologists nor geophysicists sort of owned the platform. It was a shared platform in which geophysical and geological data had equal weight and equal standing. And that's great. So it's a great tool. It's for those who've used it, I suppose it's famously more difficult to learn than classic modern implicit modeling engines. But what it does give you is a way to build a proper common Earth model shared by the geologist and geophysicist. Where its limitations were and are to a degree still, or is that it was fundamentally designed in the oil and gas business. So absolutely brilliant at seismic and geological data reconciliation. And what we've done at Mira Geoscience is try to bring other geophysical data into that. So you can run a lot of other forward modeling and inversion from GoCAD now. Some of its representations don't allow the most modern non-seismic geophysics, which is why we also use other tools now in addition to GoCAD. But the approach is simple, an iterative approach, starting data, your observed data, you build a starting model somehow, you forward model it, look at it, compare it to the observed data, do some corrections with, we use inversion to do the geometry corrections to get it closer to the observed data. And then you keep working on it until you get a final model that matches your observed data. But here you have a geological model, right? You have a model that's not all blobby. It looks like a proper geological model. This is courtesy of my colleague Glenn Pears in our Brisbane office, who's really one of the pioneers of this workflow, or maybe the pioneer of this workflow, who's been a colleague for many years now, and he's brilliant at creating these models. I want to say a few words about rock properties. Something that we'd started on, knowing rock properties were so important years ago, was building a rock property database system to analyze it. That's still going. We still use it. The idea was to be able to look at statistical distributions, as shown here, for density as a function of lithology, formation, and alteration triplets, log down the whole, to try to go from these, very high resolution wireline logs to an understanding of physical property distributions. And what this gave us was, a broad understanding of what physical properties look like across many different geological terrains. So this is Sudbury, Norites, Sudbury, which is a kind of gabbroic rock. So different kinds of norite had different distributions. The distributions tend to look Gaussian, which was good, but they really overlap a lot. So could be a problem if you're looking for discontinuities. This is from the Bathurst camp. This is physical property wireline data this is density data from a single borehole, and each of these stacked histograms is from a different lithology encountered along that borehole. So the lithologies are listed there, just hopelessly overlapping. So what do you do with this? This was really the crux of the problem. These physical property distributions overlap terribly. Yet we want to say different geological units have physical properties, and what we're looking for are these density or physical property contrasts across their boundaries. Yet the distributions of those physical properties within the units were just hopelessly overlapping. But if you take a closer look, and here's an example. This is from the porphyry copper, Mount Milligan in British Columbia. And what's shown on this slide are two cross sections. At the top is a lithological interpretation. So what we have is rock type here, and what's shown below it is alteration. And we know both rock type and alteration affect physical properties. So, some careful analysis was done here, not by us, but we're looking at the data. So this is done by Geoscience BC. And when you look at the rock properties, it's kind of interesting. So what we have here on the left is magnetic susceptibility, and in the middle, density, and on the right, porosity. So let's forget about the porosity for now, but magnetic susceptibility and density are of primary interest to connect to our geophysical data. And if we look at basalt, as we go through different alterations, least altered, potassic, sodicalcic, propylitic, okay, so different alterations, but there are differences in the distribution, but what you see is a certain pattern there, and you can say, well, basalt looks like basalt. In terms of magnetic susceptibility, you see the same in terms of density. And then if you go to a different rock type, monzonite, it's like, well, different alterations, monzonite still kind of looks like monzonite. And then if you imagine distributions over those, what you see is that, the distributions like really badly overlap, just like we see in real data all the time, yet their means are different. And this is the key thing. And this is really the key to understanding how to do this kind of an interpretation. And it's this point here. As a practical matter of interpretation, formational geological responses are geophysically separable if their physical property distributions have different means. So if you're lucky, formation A and formation B will be quite separable, by, say, density or another physical property. If you're less lucky, they'll hopelessly overlap. But as long as their means are separable, you're okay. And that answers the question of why people were able to build these kinds of models so successfully over the years before inversion, where they would painstakingly build these models by hand effectively. This is a density. This is a geological cross-section with densities attributed to each formation, constant densities. And you can see it closely follows the gravity data. And we're still doing it today. This is a paper from 2021 from the Metal Earth Project. Again, this is a geological map from around the Timmins area in northeastern Ontario. And there's a transect here that's 13 or 14 kilometers long. And that's what you're seeing here, gravity data. And again, the same sort of thing, really closely matching. So here, a geological model has been built with constant lithologies or homogeneous, not lithologies, densities, homogeneous densities per lithology, and you're able to really closely match the data. Quick example before I wrap up. So this is from the Footprints project that I was involved in, along with many other researchers, a big project that ran over several years, a few years ago. One of the case study sites was Highland Valley Copper in BC. And here we really worked hard on the Common Earth model approach. Here is a lithological model, a geological model with constant densities and magnetic susceptibilities assigned to each of the units. And here what you can see is, in the case of gravity, the observed gravity data in the top left, the density anomaly model that we built, and here you clearly see the individual geological units, even though we've allowed a little bit of blurriness because there is, of course, some heterogeneity. And then on the top right, you see the calculated gravity based on that density model here. So we're able to build a common Earth model, a model that has density attributed to it, had other properties as well. And geologists could sign off on it, geophysicists could sign off on it because the calculated gravity data based on that model match the observed gravity data. And once you have a common Earth model like that, you then have a structure or framework in which you can bring in all your other data sets, ensure consistency at all times, and then you can start combining the data. So once you've got density and susceptibility and other properties combined, you can start looking at samples. You can start using the density and susceptibility to do, in this case, targeting using machine learning or prospectivity mapping. What they were targeting here, what they used as the training data were alteration zones. They defined alteration zones from proximal to distal. That's what's shown from red to blue here as you go out. I can't remember the scale here is like 20 kilometers or 30 kilometers across there. It's fairly large. Yeah, I think it's 15 kilometers to the edge of the blue zone. The mine sits here. And so what they're trying to target is, can they learn to map an alteration zone from the data? And here you're looking at chargeability, and zone 3 and 4 are green and yellow, really different from zone 1 and zone 2. Chargeability on that axis there, right? But in order to do that, you need to get these physical properties assigned to those sample points correctly through inversion in a proper common Earth model, right? There you see it in a box and whisker plot. Again, the different alteration zones having profoundly different chargeability ranges when that chargeability model is made right. And I'm just showing you this to reflect on my comment earlier that physical properties can't be taken literally. These are lab samples from the same data versus the previous physical properties, which were from the inversion. So in situ versus lab. And the lab doesn't show the lab samples don't show the differentiation between the different alteration zones. So you got to be careful. So we took the chargeability from the inversions. Same with resistivity, you see the same sort of thing, a marked difference in the distributions as you go to different alteration zones. So again, these resistivity values are posted to these samples where we have multiple other kinds of geological data through this very careful process. It's not a willy-nilly, unconstrained resistivity inversion. And that's what I was talking about at the beginning. It's the garbage in, garbage out problem with machine learning, as an example. If you're putting resistivity or chargeability or any physical property in, you got to make sure it makes sense. And then you can combine it with other data, even trace element data, and you build a map. So you can get to these alteration zone probability maps, and I won't go into detail on that. My point simply being that if you're going to combine the geochemistry, the geology, and the physical properties from the geophysics, you need that common earth model to ensure that all of these properties are coming from one consistent model. So that's what the data taught me. The visual integration is nice, but not where most of the value lies. And really, this interpretation, modeling, validation cycle can only be solved with a common earth model. Just a quick note on the technology, which is something we've been working on for a long time. GeoH5 is a data format that we specifically designed for data integration so that you could bring geophysical, geological, any kind of data into one single data format that's portable, open, public. Anybody can use it. Any kind of software that wants to can read it. It has an API with it. It's something that we're proud to win the Innovation Award for from the AME in British Columbia 2023. It supports multiple grid types. If you're doing this kind of common earth or shared earth modeling or integrated modeling, you need to be able to represent the data in many different ways through block models, octrees, vector, raster. You've got to be able to get it all in there. And that's, again, one of the reasons we developed the GeoH5 structure. It's a structure that easily supports all of these different formats, as well as drill holes in every kind of common geological data. And then we connected that to a platform in which geophysics and geology have equal standing, which is Geoscience Analyst, which many of you know has a free reader connected with free GeoH5, and then these other tools. So this is what we're moving towards as time goes on to do this kind of integrated interpretation. So this is showing a geophysical menu. This is showing a geological menu. So for us, this is what you need. You need a platform in which the geologist and the geophysicist don't have neither has priority. It's truly a shared data structure, shared visualization, but more than that, shared processing, so you can validate and come up with a consistent model. And then finally, that's also connected to a data management system, similarly designed from the ground up to accommodate data integration, all of these different data types in the same data structures, working with the same platform shared by the geologist and geophysicist. So not to dwell on the technologies any longer, other than to say this can all be done. It's a bit of work, but well worth the trouble. And again, in any case where you're spending money, you've got geological and geophysical data, you're trying to target drill holes, you're trying to understand the ore body, this kind of approach will pay off big time for you. That's it. Thank you very much.
Thank you so much. That was so thorough. Yeah, everyone was loving it. There's some great comments coming through. So thank you for taking the time for that, John.